I want to talk about the Aufbau principle because it is the simplest one to understand. You put the electrons in the lowest available orbital at every step. And you imagine that you're just building up the electron configuration, starting with hydrogens equal to 1. And as you build this up, you go through cycles of repeating orbital type. That is to say, you will find atoms that have S1 configurations, like hydrogen, 1s1. Then you'll find atoms that have 2s1. So that's those two share chemistry. And then there'll be 3s1 and so forth. So they're repeating patterns that occur, and that's how the periodic table is arranged. So let's talk about the Aufbau principle. We start at hydrogen. We add 1 electron per element to the lowest energy orbital available. Okay, the last added electron is the only added electron, as we saw for hydrogen. That gave us 1 electron spin up in the 1s. We saw it before. So then we would start by going to helium. And for helium, we'd have Z is equal to 2, so there's 2 electrons. The first electron would be just the same as the electron of hydrogen, and the second electron would have opposite spin so as not to violate Pauli exclusion principle. Okay? So we use several different ways to represent electron configuration. After a while, it gets pretty tiresome to write out these values of quantum numbers all the time. So we have what we need to do it if we need to, but we don't necessarily, we're not restricted to that. We have other ways. There are orbital diagrams. One of them is a shorthand notation. Like hydrogen, instead of n is equal to 1, L is equal to 0, m sub L is equal to 0, we say 1s, which is what that means really, and then superscript to the right 1, which means there's 1 electron in the 1s. And if there's only 1 electron there, we follow our convention. It's got to have a spin up. Okay? Helium would be 1s with 2 electrons. 1 spin up, 1 spin down. The box diagrams representing the same thing, you have seen already. 1s with a spin up is hydrogen, and helium is a pair of electrons. 1 spin up, 1 spin down in the 1s. Okay, so if we want to go ahead from helium to lithium, now we have the 1s filled, as we mentioned before, and we have to go on up to the next available orbital. And the next available orbital, if energy is increasing from left to right, is the 2s. And so the first 2 electrons in lithium are the same as the 2 electrons in helium. Okay? And the third electron will be in the 2s, as we saw before. N is equal to 2, L is equal to 0, m sub L is equal to 0. M sub s is plus 1/2 by convention. So the box diagram, increasing left to right, looks like this. Okay? And that's the last added electron that I've made a circle for there. And so you might also see energy increasing in a vertical direction. The same electron configuration, energy increasing upwards, 1s, 2 electrons, 2s, 1 electron. Looks like that. And you can see either way. It's not hard to tell. Now the fourth electron for beryllium, we saw a few minutes ago, will add to the same 2s box that the third electron of lithium went into, but it's going to have its spin opposite now. So its m sub s value will be -2, as we saw before. And this would be the beryllium configuration. And with beryllium, we have now filled up the 1s and the 2s with our 4 electrons. Okay, step by step, there we go. Now, if we wanted to take the next step and go to the element whose Z is equal to 5, we would be looking at boron. And in this case, the first 4 electrons for boron would be the same as the 4 electrons for beryllium. And the 5th electron, the one that's of interest, is going to have to go up here in the 2p. This is the 2s, this is the 2p. Okay, that's the last one right there. So electrons in the 2p sublevel have a choice of 3 different orbitals, same energy. 3 different orbitals, same energy. So energy doesn't make a choice for us here. We can put the electron in any one of these, and what will its spin be? Plus 1/2. Plus 1/2. Spin up. So here is boron. Now 1s2, 2s2, 2p1. N is equal to 2, L is equal to 1, M sub L is equal to -1. What does that mean? Here's the second convention. Since it does not matter energetically which one of these p orbitals we choose to put the electron in, we just use a convention to put it in the -1 M sub L orbital here. Just the same way we decided to put it spin up. Doesn't mean that there's anything special about this orbital at all. We could have chosen any one, but this is what the convention is. So boron then has its last electron, and N is equal to 2. L is equal to 1 because that's a what kind of orbital? It's a p orbital. It's an orbital in a p subshell, so L is equal to 1. And M sub L now can be -1, 0, or +1. The convention says -1. Okay. So as we look at this, and we ask the next question, what about the element with Z is equal to 6? Oh, that's carbon. Carbon has 6 valence electrons, therefore. So the placement of electrons in the carbon atom is more subject to doubt, right? If you ask yourself, if we're going to put the second electron in here, how could we do it? Well, we could put it spin down in there, or we could put it spin up here, or spin down there, or spin up here, or spin down there. Okay? Hund's rules say you want to maximize the spin. Okay? The total spin is maximized by having the direction of the spin parallel. You put the second electron in with a spin that's parallel to what the first electron was. And you also don't put 2 electrons in one orbital until you have to, because why? They'll repel each other. And that will be a less stable configuration than if you allow them to be apart as long as you can. Eventually, they're going to have to go in there. But let's not do it until we have to do it. So those are part of Hund's rules. Hund's rules say in orbitals of equal energy, the most stable electron configuration has the maximum number of unpaired electrons with parallel spins. Okay, so we just put it in here. Is putting it here any different energetically than putting it over here? No. So our convention is we just sort of go from left to right, -1, 0, +1, but we know all the time they have all the same energy, and they're not really different in stability. If we put it over here, that would have the same energy as what we have right there. Okay, so that's Hund's rules, and it shows us how to proceed. The next element is Z is equal to 7. That's nitrogen. Where do you think its last electron will go? Its spin will be up, and it will be in the M sub L equal to +1 orbital. So we have 3 parallel spins, 3 electrons with parallel spins right here. That, in quantum mechanics, is a good thing because there's an effect in quantum mechanical calculation that stabilizes things if you have parallel spins. Okay? It's called spin exchange, but don't write that down. Just recognize that having all of the electrons spinning in the same direction in a set of equal energy orbitals is more stable than any other configuration. Okay, so that's nitrogen. Now we've reached the point where we're going to have to pair up these electrons, right? There's no other way to do it. The next element is Z is equal to 8. That's oxygen. And now what we do is we have to pair up, but we'll go back to the -1 and we'll pair up this one first. By convention, not by energy. Okay? So oxygen is going to have this configuration. It's 2p4. The first 3 electrons go in, spin parallel in the -1, 0, and +1 orbitals of the 2p. And so the 4th one has to go spin down in order not to violate the what principle? Pauli exclusion principle. Okay? Pick up on this, please. And then the pattern is exactly the same. Fluorine, its last electron will go spin down in the next orbital. And finally, neon will go, neon will go spin down in the last available orbital. And the 10 electrons in neon will fill up the 1s with 2 electrons, the 2s with 2 electrons, and the 2p with 6 electrons. So that is a completely filled subshell. Quantum mechanics tells us that that is a very stable situation. Filled shells are wonderful. Filled subshells are almost as good. So we need to keep that in mind when we start comparing the stability of electron configuration. That's a very stable one. Okay, so if we're going to build up electron configurations, we can do so starting now with the next the next atom after neon. Okay, neon is at the end of the second period here. Let me see if my periodic table works. Sometimes it does, sometimes it doesn't. Okay, it did this time. So here's neon. We just finished the 10 electrons filling up neon. And then if we go over here to number 11, it's at sodium. And this is 3, the third period, 3s1. And if we go another step, magnesium would be 3s2. Okay, this is the S1 column here. 1s1, 2s1, 3s1. This is S2. Magnesium would be 3s2. So if we look at the third period, the sublevel energies we pointed out before are 3s is more stable than 3p is more stable than 3d. In terms of the energy, 3s is most negative. So sodium would be 3s1 and no other electrons here. The full electron configuration of sodium would be the neon configuration 1s2, 2s2, 2p6 plus 3s1. And a little bit later we'll start calling this the valence of sodium. The outermost electron of sodium is 3s1. And then these would be called core electrons. They don't play any role in chemistry. They play a role in physics, but not in chemistry. So a condensed or shorted, can't think of the word, shorthand kind of notation would be neon 3s1. And I know you'd all much rather write neon in brackets in 3s1 than you would brackets 1s2, 2s2, 2p6. But sometimes it's necessary to do the full electron configuration. So you need to learn it both ways. Magnesium, Z is equal to 12. Its last electron will go into the 3s as well, but it will be spin down. So it'll be 1s2, 2s2, 2p6, and 3s2 now. Okay, are you bored yet? Okay. In the last electron that's added to aluminum, silicon, and phosphorus, which are 13, 14, and 15, fill halfway the 3p subshell. And it's exactly the same as the 2p subshell. Here's what it looks like. Here's aluminum, 3s2, 3p1. And so it's spin up. According to our convention, it's spin up. And this particular orbital is m sub l equal -1. This is 0, and this is +1. So we fill this 3p subshell just like we did the 2p subshell. Nothing new to learn there at all. So aluminum, 3s2, 3p1, looks like this, the box diagram. Silicon is 3s2, 3p2. It's very much like carbon. Carbon was 2s2, 2p2. Silicon is 3s2, 3p2, as you can see over here. Phosphorus is under nitrogen in the table, and its last added electron will go into m sub l equal +1. All the spins will be parallel, and this will be a exactly half-filled subshell, which we call the 3p subshell. All right? So far the 3s and the 3p look pretty much like the 2s and the 2p. And we could clean the whole thing up with sulfur, chlorine, and argon. Sulfur will be 3s2, 3p4, and it will look just like oxygen did, spin down in the m sub l equal to -1 for the last electron. Then chlorine will have one more electron. That'll be spin down in m sub l equal to 0. And finally, argon is the next noble gas. It will have its last electron spin down in the m sub l equal to +1. And so argon is 1s2, 2s2, 2p6. That's a filled n is equal to 1 shell, a filled n is equal to 2 shell, and a partially filled n is equal to 3 shell with 2 filled subshells. That's a good thing. That makes the atom even more stable and less reactive. Okay, so here's where we are. Here's a skill. Write a set of 4 quantum numbers for the 3rd and 9th electrons in neon. Okay, we just saw neon. So neon is 1s2, 2s2, 2p6 in the shorthand diagram here. In the box diagram, here's its 1s2, and here's the 2s and the 2p. So the 3rd electron will go into the 2s. The 4th electron will fill the 2s. The 5th electron will go spin up in the m sub l equal to -1, 2p. The next electron goes spin up in the 0. The next electron goes spin up in the +1. The next electron goes spin down in the -1, makes a pair, then another pair, and then another pair. Isn't it cool how I did that? I hate to tell you how much hair I lost trying to make that happen. Okay? I was pulling it out. So the 3rd and 9th electrons, the 3rd electron is that one. And you could see from this, it's n is equal to 2. It's an s subshell, so L is equal to 0. And m sub L is equal to 0. And by convention, m sub s equals +1/2. So those are the 4 quantum numbers for the 3rd electron in neon. Questions? Okay, what about the 9th electron? Well, it goes in 1, 2, 3, 4, 5, 6, 7, 8, 9. It's that one right there. Okay, now you could see that n is equal to 2. You can't you? N is equal to 2. No, that's not. 8 would be this one over here.
It's 2, 4, 6, 8.
Count them the way they go in. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the Aufbau principle. We just went over it. You didn't forget it already, did you? You got to count them the way they go in. And so that one will be in the m sub l equal to 0, 2p atomic orbital. So it'll be n is equal to 2. There's the 2. L is equal to 1. It's a p orbital. We knew that. M sub l is equal to 0 because that's the 1. And m sub s is equal to -1/2 because that's our convention. First one positive, second one negative. We had shown via the Aufbau principle that we had a periodic table or periodically repeating electron configurations in the vertical groups in the periodic table. And here are the first three periods. And if we look at group 1A, we showed that hydrogen is an S1 configuration, lithium is an S1 configuration, and sodium is an S1 configuration. That means that each one of those elements, their atoms show one outer electron to the world. So it shouldn't be too surprising that they behave very similarly, because they're presenting the same face to the world. If we look at group 2A, they're S2. If we look at group 7A, they're S2P5. 2S2, 2P5, 3S2, 3P5. That's the way the table is arranged. So we can take advantage of that, and I'll be showing you how to do that today. The outer electron configurations then correlate closely with the chemical behavior in any one of the vertical group's elements. Remember, groups, periods. The group 1A elements have outer electron configuration of noble gas NS1, where N is some integer. And as such, the attainment of a noble gas electron configuration, noble gas electron configurations being among the most stable, involves the loss of one electron. So that would mean for M being the requisite element here, we would see for these 1A elements things like sodium chloride, metal with one metal cation, chloride anion, or M2O, or M2S. The loss of one electron is one of the things that you expect for this. It's the main feature of the chemistry of these elements. On the other side of the table, group 7A is one electron short of a noble gas configuration, which is S2P6. These elements have S2P5. So the halogen elements of group 7A have in their ionic compounds mostly X minus, F minus, Cl minus, Br minus as their stable state. So if we recognize that, it's pretty easy not to have to memorize very much about the properties of these compounds, because you can, in some cases, sort of figure them out. Okay, we are now then finished with the third period, and it's time to talk about the fourth period. Remember, in the Aufbau Principle, we are step by step filling up the orbitals upwards in the sequence here. Upwards in the sequence. Aufbau. My pad is about to fall off onto the floor. Now, as we go along here, we have finished the 3P last time. And that is element number 18 is argon. At argon, we filled up the 3P. So we asked the periodic table, where's the next element? So we look for 19. So where's 19? Well, it's clear over here on the other side. Potassium down in the fourth period. Okay? So in the filling sequence here, remember these are S1s. So that would mean potassium would be 4s with one electron. That would be its outer electron configuration, if you would. Okay, here it is right here. Now we're going to go across, and at the beginning of the next section here, this will be the 3D family or group of elements here, where the 3D orbitals are being filled. And what we'll see here is in the fourth period, the 3D orbitals are filled right after the 4s. Here they are right here. Here's the 4s. The next one, which is not very far above it, is the 3D. Okay, so the 4s sub-level energy is below the 3D. So as we go along here, element 19 says fill the 4s with one electron, Element 20 says fill the 4s with 2 electrons, and then we're going to go on to 3d. 4s before the 3d. Okay? Here's the comparison of the two. So potassium, Z is equal to 19, has argon, which is 18. Z is equal to 18 plus 1. So there's 1 electron that will go in the 4s. So potassium has a 4s1 configuration, 1 unpaired electron in its atoms. Calcium is Z is equal to 20. And the next place where an electron can be is still in the 4s, but it's going to have to be spin down in order not to violate whose principle? Pauli principle. Pauli exclusion principle. Thank you. Now, the next step is scandium. Z is equal to 21. And scandium is the first member of the transition elements where the 3d orbitals are being filled. And so we will do, since the 3d is a little bit above the energy of the 4s, we will put 1 electron into the 3d. So scandium outer electron configuration is 4s, 2, 3d, 1. Okay? Oh, it's not too surprising. The next one should follow Hund's rules, and by convention, it will be the same spin as this one here, and in this is m sub L negative 2, this will be m sub L negative 1. So titanium, the next element, Z is equal to 22, is 4s2, 3d2. Everybody comfortable with that so far? All right, now while we're going along here and building up the size of Z, the 4s is coming down in energy faster than the 3d goes down. Please don't ask me why. I don't know, but that's exactly what happens. So the net result of that is they're getting closer and closer together in energy. So eventually we're going to run into a problem. We make it to vanadium, 4s2, 3d3. That looks good. And so we're over here at vanadium. The next element is chromium. All right? So we go back here. It's titanium, vanadium. And what electron configuration is expected according to the Aufbau rule for chromium? Well, according to Aufbau, if there's still enough difference in energy between the 3d and the 4s, this ought to be, for chromium, 1 more electron in the 3d here. That would make, if we put that electron right there, that would make 4 unpaired electrons for the chromium atom. Here's where we hit a snag. Chromium in the laboratory has 6 unpaired electrons, not 4. And what's happening here is the Aufbau principle is not controlling at this point. The principle that's controlling is the stability of half-filled subshells. So with 6 unpaired electrons, this chromium constitutes an exception. And you're going to have to memorize it unless you can figure it out. The exception is that chromium will be 4s1, 3d5. The important thing is to realize how stable 5 unpaired electrons are if they all have the same spin. Remember we talked about the spin exchange energy? Well, exactly a half-filled subshell arranged like this is quite stable. And it is stable enough to where the Aufbau principle doesn't predict things correctly. So this is an exception. Right? Questions on the exception? Well, we will see.
I have a question.
Yes, go ahead.
Is that going to hold true for all 6D?
I'm sorry, I didn't hear the last part.
All the elements of group 6D?
It will hold true one more step down. I'll show you that in a second. So this chromium is going to end up 4s1, 3d5, and the next element below it, if we look in the periodic table, is molybdenum. Molybdenum has the same exception. If you go down to, that's 3D, 4D for molybdenum. If you go down to 5D, all bets are off because that involves F orbitals. So I'm going to give you a break. I'm not going to ask you to learn the electron configuration of the elements in the third transition period because there's no simple way to predict them. Dr. Bott and I disagree on this. If we look at the rest of the 3Ds, the steps work just fine for a while again. The next electron comes from manganese, and it goes into the 4s 4s subshell, 4s orbital, and you get 4s2, 3d5. That shouldn't be surprising. It maintains the stability of these 5 parallel spin electrons. Okay, so manganese is 4s2, 3d5. Now with iron, we got one more electron. We have to start pairing up the 3Ds. So iron will be 4s2, 3d6, cobalt 4s2, 3d7, nickel 4s2, 3d8, and then something happens. Then the next element is copper. And copper has one unpaired electron, which you would expect. If you followed the Aufbau thing, you would say this ought to be 4s2, 3d9. Okay? You'd expect 4s2, 3d9 for copper, which would have one unpaired electron, but it would be in what subshell? The D subshell. The D subshell. That's where the unpaired electron would be. And if you'd like to, you ought to write out a box to show that. Write out the box diagram. Experimentally, it does have one unpaired electron, but it's in an S orbital, not a D orbital. So that's another exception. We'll draw a box around it to remind you that it is an exception. Okay. Now the last of the 3D elements is zinc. Z is equal to 30, and it's 4s2, 3d10. And that is an extremely stable electron configuration, 3d10. Yes, go ahead.
Okay, so for copper, would it be 4s2 or 4s1?
The thing is shown here. This is the 4s, so it's 4s1, 3d10.
Okay, so it says except 4s2?
We would expect, if you were going down through here, you would expect 4s2, 3d9, but that's not how it turns out. So again, the same pattern holds below copper one step, and that would be in silver. So silver would be 5s1, 4d10. Okay. So 2 exceptions, 2 Aufbau exceptions, and you need to memorize them for chromium and copper, molybdenum and silver. Questions? Okay. The reason ultimately for these things is the extra stability of half-filled subshells and completely filled subshells. And the more orbitals there are in the subshell, the bigger a deal it is. The 4p subshell remains to be filled. We did the 4s and the 3d. The 4p is next as we go up, and it is filled in exactly the same way as the 2p and the 3p. Gallium has one 4p electron, germanium has 2, arsenic has 3, all unpaired. Then we start to pair. Selenium has a pair and 2, bromine has 2 pair and 1, and krypton has 3 pairs. So that gets us all the way over to krypton, 36 elements, and we are about as far as we need to go in looking at the pattern here. Do you have any question about filling of the subshells in the electron configuration up to 36? Okay, the periodic table is going to help you work these things out. Now there are some pieces of nomenclature, words that we use here, and I've called them features here because that's a popular thing to do. They are actually things that you'll need to learn. The inner or core electrons are those in the previous noble gas plus any completed transition series. Okay? And that's opposed to the outer electron, which are those in the highest energy level. So to give you an example of the latter, we have, let's take sulfur. Let's take sulfur. Sulfur is, Z is equal to 16. So we would start off 1s2, 2s2, 2p6. That gets us to through the second period. And we have expended 10 electrons here. Then 3s2, that's 12. And we need 4 more. They'll be in the 3p4. Now, as you look at this, the outer electrons are those in the n is equal to 3 level. And the inner or core electrons are the 1s2, 2s2, 2p6, which corresponds to neon. Okay, so they are the electrons that go with the neon noble gas. They are, the inner electrons are completely unreactive as far as chemistry goes. Only these outer electrons participate in chemical bonding and reactions. So that makes life nice. We don't have to remember very much about these inner core electrons, except maybe how many there are. All right? The valence electrons, valence is a more general term, at least in my view, and valence electrons are those that may be involved in forming compounds. When it comes to main group elements, the valence electrons are the self-same electrons as we said the outer electrons were. In other words, in sulfur, the valence electrons are 3s2, 3p4. In the case of the transition elements, it's a little bit more chancy. If we are talking about a compound of iron or cobalt or nickel, the 3d electrons can play a role in the bonding of, let's say, cobalt trichloride. Right? So if that's the case, for these elements, the d electrons are valence electrons. But as we get over here to zinc, the d subshell is filled. And once the d subshell is filled, that's a completed transition series, and those electrons become inner electrons once they're filled. If they're not filled, then they are valence. But if the subshell is completely filled, 3d10, 4d10, 5d10, then those are judged as inner electrons or core electrons. Does that make sense to you? All right, so those are the rules. Let's do some examples. Give the full and condensed electron configuration, the partial orbital diagrams, which are just box diagrams, for the valence electrons, and the number of inner electrons for strontium, Z is equal to 38, and molybdenum, Z is equal to 42. Let's go and find them on the table. 38 is here. It's in the 1, 2, 3, 4, the 5th period. There it is. And remember the first group, vertical group on the left is S1, and then S2, and this would be P1 over here, and so forth. So there's strontium. And the other one was, what was the other one? Molybdenum. Oh, thank you. It went out of my head like a vapor. Okay, there's molybdenum. So they're both in the 5th period. And strontium looks like it will have 2 s electrons of the 5s variety. So we know something about it. Molybdenum, on the other hand, is right below chromium, so it's going to have the same exceptional pattern that chromium does. Okay, so let's erase this, go back, and look at the electron configurations. Now, what I want to do is I want to show you how to build this up, because that's the critical thing in electron configurations. If you can't build this list up, everything is going to go downhill for you when you try to do the homework in Chapter 8, 8, 9, and 9. So I want to show you how to do it. Let's go back here, and we're going to do strontium. And here's a very nice little tool or idea that you can use. As you go through the periodic table, following the Aufbau principle, what I want you to do is to take your periodic table. What I recommend is you maybe re-Xerox it and make some space just to the right of it. Thinking space, he said. All right, so now what I'm going to do is I'm going to write down the contributions, I mean, of the each one of these periods to the electron configuration. So the first contribution would be 1s2, hydrogen, helium. The second period contributes 2s2, 2p6. Okay, and you see the method to my madness here. The third one would be 3s2, 3p6. And remember, we're going down here. The fourth one would be 4s2, 3d10, 4p6. Okay, that's the P. And that's 36. Strontium is 38, so this would be 5s1, 5s2. Okay, you write them all down, then you just write them together, add them up. That's all there is to it. You'll always have the periodic table on your exams and when you're doing your homework and so forth. So if you remember to do that, it's easy to remember the S block, the D block, the P block. And if your periodic table doesn't have the period numbers written down, write them down. And that's how you can do it. Questions on that? Remember what it looks like. How do you check yourself? Add up the number of electrons. 2 and 8 is 10. 8 more is 18, 20, 30, 36, 38. They got to add up to the 38 that we have for strontium. If they do, you got that part right, most likely. Okay. If we go back, uh-oh. Now I messed it up. Sorry. Hang on just a second. So here is strontium, 38 electrons, the full electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. That's the full. It also says the condensed. So that would be krypton, 5s2, krypton being the nearest noble gas. How many inner electrons? The same number as krypton, 36. And that's that. Questions on strontium? The partial box diagram then is for the outer electrons. Strontium would be in the fifth period, so it's 5s2, 4d10, 5s2, 4d nothing, 5p nothing. Okay, that's the box diagram. Any questions on strontium? Are you comfortable with this? Can you do it? Sure you can do it. I know you can do it. You use this method, you'll have success. All right then, molybdenum. Molybdenum lies under chromium, so it has the same exceptional pattern as we talked about. Here's molybdenum right here. So if we're going to do the electron configuration, we'll start at the top of the table, and 1s2 for the first period, 2s2, 2p6 for the second period, 3s2, 3p6 for the third period, just like strontium. Now we have 4s2, 3d10, 4p6. Okay? And then 5s2, 3d4. Uh-oh, wait a minute. That's not right. It's under chromium. So it's 5s1, 4d5. 5s1, 4d5, 6 unpaired electrons. So then you add all these together, and you got the full electron configuration for molybdenum. And the outer electron, or the valence electron configuration is 5s1, 4d5. And the box diagram, let's see, condensed electron configuration would be krypton, 5s1, 4d5. So I'll write that down for you. Krypton, 5s1, 4d5. Any questions with that?
Why is it not 4d4 on molybdenum?
For the same reason that chromium wasn't 3d4. Filled or half-filled subshells are more stable than partially filled. Good question. Thank you. Okay, then the number of inner electrons is that of chromium, so that's 36. And the partial orbital diagram. This will be the 5s. And then, if I can draw it properly, the 4d and the 5p, right? And this is 5s1, 4d5, so we put one electron spin up, following the convention, in 5s1, right, in 5s, and then 5 electrons spin up into 4d. And that is the box diagram, or more properly called the partial orbital diagram for the valence electrons. How are we doing here? Yes, go ahead. Do you have to draw what? If it's completely empty, probably not. I just did it for completeness, I guess you could say. Other questions? Question? Yes.
The orbital, the boxes, how come the D has 5 and D has 3? The boxes here?
These boxes, the 5s1 and the 4d5?
Yeah, D has the same 5 boxes as D has 3.
Remember what L is for a D subshell. Do. 2 for L. So what can, if L is 2, what can M sub L be? Plus 2, plus 1, 0, minus 1, minus 2, 5 of them. 5. And that's why there are 5 boxes here. L is equal to 1 for a P subshell. So it's plus 1, 0, minus 1. We've got 3 boxes there. If you remember the relationship between the quantum numbers, you can figure this out. Okay, let's go ahead. Write the electron configuration of these main group ions. Okay, now we have to hark back. We learned how to predict ions way back in chapter 2, actually. And they want the condensed electron configuration and to write reactions for the formation of the common ions of iodine and potassium. Iodine, I remember, is in group 7. Potassium is in group 1A. So, in general, the ions of the elements in group 1A, 2A, 6A, and 7A are isoelectronic with the nearest noble gas. It means the ions have the same number of electrons as the nearest noble gas. So we'll use that as our basis for writing the equation. First of all, before we write the equation, here's iodine down here. And if you go through the same process we just did, it is krypton, and of course I've left out some things here. It's krypton 5s2, 4d10, 5p5. That's iodine. And the ion, that's the iodine atom. The ion is going to have the same number of electrons as xenon. There are 53 electrons in krypton, 36, and 2, and 10, and 5 is 53. We add 1, it'll be 54. That's the same as xenon. So this will be krypton 5s2, 4d10, 5p6. Okay? So we use the noble gases to tell us how many electrons to add or subtract from the atom in question. Potassium is over here on the far left side, and it is in the 4th period. Its nearest noble gas is argon. Potassium is 19, argon is 18. So potassium will be argon plus 4s1. And the ion of potassium will be a positive ion because the closest noble gas is argon. It has 18 electrons, so potassium needs to get rid of 1. So it loses 1. The potassium ion has 18 electrons in the argon configuration. So that's how we figure out the electron configuration of elements from group 1A, 2A, and 6A, and 7A.